Good day, mateys. Welcome to Electron Transitions, the tale of the moving electrons. Written by Light Emitted. So when we start looking at electron transitions, we're looking at essentially the movement of electrons, how they are getting from one place to another in those energy levels. So if you take a look at these electrons, notice we have the 2 in the energy level 1, where we know that only 2 electrons can go. But they don't always like to stay there. Sometimes atoms get energy that comes in and energizes those electrons. Then they have too much energy to stay in this lower energy level. They have to move. So when atoms absorb energy, the electrons have to move into what kind of energy levels? Well, obviously they're absorbing energy. They have to go into the higher energy levels. So they absorb this energy and they come out to higher energy levels. It's not always the same one. Sometimes it's very random. It just depends on how much energy they absorb. But they don't always like to stay out there. It's kind of like if they went on vacation. They're not going to stay out here in these other orbitals for very long. So then they lose energy. And so when they come back down, so if this electron were to go out and then come back down to its ground state or its home base here, it has to give that energy back. And when it gives that energy back, it shoots it out as light. It can't keep that energy, has to get rid of it. So when we're looking at light, there are lots of different types of light. And the electromagnetic spectrum helps us kind of understand all those different types of light. So if you notice here, we have gamma rays, kind of like the little green Martian man that shoots his little gamma ray gun in the cartoons. X-rays, ultraviolet rays. This space right here comes down to visible light. We have infrared light, microwaves, and radio waves. All of these different types of waves are all light. You didn't even know it, but when you listen to the radio, you're actually listening to light being transmitted through your speakers. When nuclear radiation gives off gamma rays, it's essentially high energy light. When you cook your food in the microwave, you're cooking your food with light. Infrared light is just known as heat, and heat waves are a form of light. Ultraviolet light, or UV light, is what gives you sunburns. All these things are just waves, and they're all considered light. And now the electromagnetic spectrum tells us a lot of information. So up here we have wavelength. As we go to the right, the wavelength increases. So these radio waves are really big. They're really slow. They're like the throwers on the track team. They don't move very fast. But down here, these gamma rays are really fast. They're like hyper little toddlers that can't stop moving. Super duper fast. Now it also tells us about energy. Now, in addition to these waves being very small, they're very fast. That means they have a lot of energy. So energy is increased down towards the gamma rays. Again, if we go towards the radio waves down here, they're really big, they're really slow, not a whole lot of energy. Now, one thing that isn't on here is the frequency. It doesn't quite show you the waves of the frequency, but it shows you down here. So if you notice, here's 10 to the 20th, here's 10 to the 4th, so the frequency of these waves happens a lot more with the gamma rays. They're going by a point a ton more times than what these really slow radio waves are. Also, I want to mention this visible light. One way to remember the order in which it goes is Roy G. Biv. So red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv. All right, so as we're talking about this light, all light travels at the same speed. Whoa. But we just talked about how it had different energies and different frequencies and different wavelengths, but it's all traveling at the same speed. So the light that you cook with in your microwave, traveling at the exact same speed as the radio you listen to, traveling at the exact same speed as that gamma ray gun by little Martian dude. But the things that are different are those three things we talked about. The frequency is different, the wavelength is different, and the energy is different. But it all has the same speed. So when we're talking about frequency, we're talking about how often the waves pass a given point. So here, if we were to time this 10 seconds, there'd be a lot of waves that passed by. In this one, this is one wave. There's only a few waves that pass by. So this one would have a higher frequency. And frequency is designated with something that looks like a V. Now wavelength is how long the wave is. So from crest to trough, and when it crosses that line again. So crest is how high it goes, a trough is how low it goes, and then when it crosses the main line, that's your wavelength, how long those are. So this one has a very long wavelength. This one has a very short wavelength. Okay, see the difference? We designate wavelength with this goofy little thing that looks like this. If you really want to, you can kind of make it look like a dinosaur. Rawr. And the last thing that it also has is energies. Remember, lots of these waves have a lot more energy than these big, slow waves. Now we can put these together by saying that the speed of light is equal to our wavelength times our frequency. And the speed of light, remember it's the same for all types of light, is 3.0 times 10 to the 8th meters per second. I will not make you memorize this, you will have it, but you will use it a lot. So it would be a good number to keep in your mind. So we designate the speed of light with c. So whenever you see c, kind of like E equals mc squared, that always means the speed of light. So the speed of light is equal to wavelength times frequency. So let's give that a go. We know that our speed of light is equal to wavelength times frequency. So what is the frequency of light with a wavelength of 8.7 times 10 to the negative 7th? Well, we know our speed of light is 3.0 times 10 to the 8th. We know that our wavelength is 8.7 times 10 to the negative 7th. And we are looking for V, or frequency. So all we have to do in order to solve for V is divide by 8.7 times 10 to the negative 7th. So this is, again, somewhere where you're going to have to use that scientific notation key on your calculator. Some of you might have an EE key or an E key, but wherever it is, we found it a while ago. So if we do that math, it turns out to be 3.4 times 10 to the 14th. Now the units for frequency are always just per second. How frequent something happens is how often it passes by, or how often something happens. So 3.4 times 10 to the 14th per second. Let's try another, let's try another. So if we look at this one, electromagnetic wave has a frequency of 4.62 times 10 to the 14th hertz. Hertz means the same thing as per second, so you might see that both ways. But you want to find the wavelength this time of the wave and express it in nanometers. So we know that, again, our speed of light is equal to our wavelength times our frequency. So 3.0 times 10 to the 8th is equal to our wavelength that we don't know times 4.62 times 10 to the 14th. So again, all we have to do is divide that out and see what we get here. Remember that the units on this one are in meters. So 3.0 times 10 to the 8th divided by 4.62 times 10 to the 14th, and we get 6.5 essentially times 10 to the negative 7th. Because our wavelength or our speed of light was in meters, this one is also in meters. So we want to put this into nanometers, because nanometers are going to help us figure out what color of light this is, because that's what our visible light is measured in. So if we think about this, we have 1 times 10 to the negative 9th meters in 1 nanometer. Nano, negative 9 is how you can remember that. So if we divide that by 1 times 10 to the negative 9th, we get 649.4 nanometers. Now if we were to then look at our electromagnetic spectrum over here, what color would that be? Well, here's where our nanometers come in. Remember that visible fits in right there. And so 649, here's 600, so we're looking at about right there. We're probably looking at an orange color of light with that wavelength. All right, so that related wavelength and frequency, but remember that we also had energy, and energy also can change even though the speed is staying the same. So we know that energy is related to our Planck's constant times our frequency. So this really old smart guy again came up with this Planck's constant to relate light and energy and energy and frequency. So this number is always the same. Again, I won't expect you to memorize that, but it is a number you might want to keep in the back of your head. So our energy is equal to Planck's constant times our frequency. Let's give it a go. So we know our energy is equal to our Planck's constant times our frequency. So we know that Planck's constant is 6.626 times 10 to the negative 34th. And our frequency this time is 7.5 times 10 to the 14th per second. Therefore, our energy, plug that into our calculators, is 4.97 times 10 to the negative 19th joules. Then, all right, now let's look at how this kind of relates to our electron transitions. We know that all atoms have differently spaced energy levels. So if we're looking at helium, its energy levels may look pretty evenly spaced out, whereas if we look at something like, let's go strontium, its energy levels may look a lot different. Some may be close, some may be far away. Don't laugh at my really bad circles, but they're all different. So this is like a fingerprint, because we know that when electrons move, in every element they're going to be moving different distances. So we can figure out what those elements are by measuring those distances. Well, those different distances mean that the electrons have different energies. Moving from here to here doesn't take as much energy as in this element. It has to move further away. Okay, every distance has an associated energy with it. It takes me a lot more energy if I were to run to Sydney than if I were to run to Brule. So those different energies means that they also have different frequencies. Means they also have different wavelengths, because all three of these quantities are related. So that means different energies, different wavelengths, different frequencies. That means that there are always different types of light when those electrons that have absorbed energy fall back down. Remember, they absorb energy to go out, and then they have to give it back. And so when they fall back down, they give that energy back as light, and it's all different types of light. So let's look at this for a second. Maybe. All right, in this example here, we have an electron orbiting a nucleus. Energy comes in, and it shoots out. So here, energy came in, and it absorbed, and went out to a higher energy level, and then it shot back out and let that light out. Let's make it some higher energy that's coming in. Shoo! Higher energy that came in, it shot it further out. When it dropped back down to its home base or its ground state, it let that energy back out as light. Okay? Again, if you have any questions, let me know. Otherwise, I will see you in class where we'll discuss this some more. Peace.